Hello, good morning everyone. Yes, okay, so we're going to continue on with this story about integration, integrating functions of multiple variables. Okay, so integrating over regions in the plane now. Okay, so let's do sort of a warm-up exercise where we integrate over a rectangle. Welcome, hello. Let everyone get seated there. Take a moment to arrive. Okay, so with these things, I think it's helpful to remember what this thing's calculating. So this is calculating a volume for us. So this is the volume under the function x plus y, and above the rectangle what's the rectangle here? X is going between 2 and 4. And y is going between 0 and 1. Okay, so there's sort of a plane, and we're looking at the area under that plane. Okay, so let's calculate this thing. Okay, so we're here. We note that the inner integral is in x, so we're going to find the antiderivative in x. So that x will turn into a half x squared. That y will turn into a y times x, and we'll go between 2 and 4. Okay, so that handles the inner integral for us. Now we apply fundamental theorem of calculus with these bounds. And what do we get? We get we plug in our bounds and we get this expression here. So this 4 squared, that'll be 16, divided by 2, that'll be 8. 2 squared will be 4, divided by 2 will be 2. Okay, and now we've got it down to a place where it's a one variable integral, 0, 1. And that will be 6 plus 6y dy. Oh. Yes, very good. So that will be a minus 2y there. So we get plus 2y here. Oh, whoops. Sweet. Good typo catch. Okay, so we continue on with this guy. Okay. Now we go between 0 and 1. Plugging in our upper bound, we get 6 plus 1. Plugging in our lower bound, we get 0. So our total answer should be 7. Okay, the area under that object should be 7. There was a very interesting question asked last lecture about what happens if we switch the order of integration, right? If we, instead of doing dx dy, we do dy dx. So I want to investigate what happens there. Okay, so now we'll change the bounds of integration. Okay, and I guess the idea here is if we switch the order of integration, we should be measuring the area of the same thing. Okay, we're measuring the volume of the same region, but written down in a different way. So let's try that and see what we get. That will be in that order there. Okay, so notice that the bounds for x have stayed with x, and the bounds for y have stayed with y. Okay, so we've switched dy and dx, and we've switched the integrals. Okay, so what do we get? So integrating in y, we get this, right? So we treat x as constant, y becomes a half y squared. Now we plug in our upper bound y equals 1, so we get x plus a half dx. And then the lower bound 0 would give us a 0. Okay, so now we integrate this guy. Between 2 and 4. Okay, so applying fundamental theorem of calculus, we plug in our bounds at the ends, and we get 8 plus 2 minus, uh-oh, that doesn't work, so that's 16 over 2 is 8, plus 2 minus 2 plus 1. Okay, so we get 10 minus 3, 7. Okay, so there's something going on here. If we switch the bounds of integration, we get the same answer both ways, which is kind of surprising. Okay, so our observation is that these two orders of integration give the exact same volume. Okay? So this is a nice fact. We're going to explore this a little bit more today. Are there any questions so far about that calculation? How the setup for that calculation goes? Okay. So we'll get more into this aspect of changing order of integration later. But right now, I want to generalize away from rectangles. So far, we've been integrating over these rectangles. And now I want to introduce the tools to integrate over more general regions in the plane. Okay. Okay, so let's head in the direction of more general regions. So we're going to introduce a definition. Okay, we're going to say that a region is Y simple if there's a pair of continuous functions such that the following thing happens. So if there's a pair of continuous functions such that our region is bounded by those two functions. Okay, such that our region is contained between the graph of those two guys. So what does a Y-simple region look like? We're somewhere in the plane. We've got a function here, f2 of x. We've got a function here, f1 of x. And our region is the guys bounded by those two functions. Okay. So we're going to say that something, so that's what Y simple means. Are there questions about that definition? Yes?
Why is it called Y simple?
Right. So the way to interpret this is that the y coordinate is sort of bounded by two continuous functions. So So it means that the y-coordinate of your region is simple in some sense. It's not, oscillating really wildly. There's no big jumps or anything. Continuity is kind of a simplicity condition. Yeah, nice question. A lot of things in math, they have etymologies, and we can understand the concepts better by thinking about those etymologies, or why would someone call that simple? Sweet. Okay. Okay, we're going to say that something is x simple if a very similar property holds. Okay, so we'll say the same kind of thing, but now in the x-coordinate. If we've got two continuous functions that bound our x-coordinates. Okay, so here the picture is something more like this. We've got a region bounded by two continuous functions. Okay. So those are some terms. Okay, just to get a handle on these, can anyone think of a region that's not y-simple? Where there are no functions such that we can do this thing? So I find it anytime I get a definition in math, I do two exercises. The first one is I think of an example of that thing, and the second one is I think of a non-example. Okay, so let's think of an example first. So we want some graph that bounds our region. Okay, so let's take something like this. Yeah, so this is y-simple. Right? I believe that that upper curve is continuous. I believe the lower curve is continuous. So we're y-simple. Okay. And now could someone think of a region in the plane that is not y-simple? Yes?
What about the entire plane?
Ah, mathematician move, yeah. Yeah, sure. Right, now there's no function that bounds my region. Right, yeah, very good. Sweet. Okay, that's a nice example. Another example I want to point out is simple regions can't have holes. Okay, so another non-example would be something like this. Okay, there's no pair of functions that would give us that region. Right, because we've got these sort of four, in any vertical line, we're going to have 4 points, which is too many points for two functions to give us. Okay, so there's a couple pairs of non-examples. So when you're thinking why simple, you want sort of like sort of a blob with continuous boundary. Okay, sweet. Okay, so if we want to integrate over a y-simple region, okay, we'll often write that in the following way. Okay, so this is the integral over the region of this function with respect to area. So this guy here, dA, okay, when we put dA, it means with respect to area. Yes?
So it's all kind of like underneath both integrals in a sense?
Yes, typesetting challenge. Yeah, it's written kind of underneath both integral signs. Yeah. There's a common thing among math people that they get really into typesetting. I don't know why, but I think something about math notation requires you to put symbols in weird spots. Okay, so dA means with respect to area, and we're going to see that dA is equal to dx dy or equal to dy dx. Okay, we've seen that you can write this down with either one of those setups. So this integral over a region of this function with respect to area, we can write it as a integral where if we're y simple, we have control over the y coordinates. Okay, so let's say x runs from A to B, and now y will run from F1 to F2. Okay, so we integrate in y between the bounds that the simple region gives us. Okay, so let's do an example of one of those. Okay, so we've got a particular triangle here, and we want to integrate over that triangle. So we should figure out what that looks like. Okay, so the region will have vertices so it's got a vertex at 0, 0, a vertex at 1, 0, a vertex at 0, 1. Okay, and now it's not clear if this region is simple or not, so we should introduce some functions that are the bounding functions. Okay, so here we've got a straight line that bounds our region, and that's the line y equals 1 minus x. And then here our bounding function is y equals 0. And the region that we want to integrate over is the inside of that triangle there. Okay, so to set up this integral now, according to our formula, right, this will be the integral in x between 0 and 1. And then the integral from 0 to 1 minus x, which is our upper bounding function. And then we get this guy here. Okay, sweet. Okay, so let's calculate this thing out. So we take the antiderivative of the guy inside. We get here, substituting in our bounds. We get here. I find it helpful to multiply these kinds of things out before we integrate in x. Okay, and now integrating in x. We get here. Okay, and now we plug in our upper and lower bound. Get something like this. Okay. And then what should we put this over? I guess 12ths? Okay, so we get -2 plus 3, so we get 1/12. Yay! It's a 24th, which is the best number. Actually, 24 is the best number. Anyway. Okay, sweet. So this is how we integrate over y-simple regions. Okay, we plug in the bounds in x, and then we plug in the continuous functions that make us y-simple in the other direction. Okay, so now I want to define what it means for a region in the plane to be simple. Okay, so we say that something is simple, full stop, if it's x simple and y simple. Okay, so this means that we're bounded by continuous functions in both directions. Okay. Okay, so I would like to do just a couple examples of how to set up these integrals. So we won't do the full calculation, get the full number. We'll just do the setup. Yeah, so let's just see what we would integrate without going through and integrating the whole thing. Okay, so okay, so we'll set up this integral, and let's set it up in both ways. Okay, so set up the integral of f of xy over the region bounded by the parabola and the line using both orders of integration. Okay, so let's do this one first. Okay, so it's important to know what the region looks like. So we put in a parabola. There's y equals x squared. And we put in a line. There's y equals x. And then the region we care about is this small region right there, where the two curves meet. Okay, so using this order of integration, right, what do we want to do? We want to go as far as possible in x. Okay, so we have to figure out the horizontal limit, the x limit of this guy. So to do that, we solve for where they meet. Okay, so they meet at x equals 0 and x equals 1. Okay, so our bounds of integration here will be between 0 and 1. And our region is set up in such a way that it looks y simple. We've got these two bounds on the y coordinates here. So we'll put in those bounds. And we get that guy. Are there questions there so far? Any comments? Yes?
So this is just for an arbitrary function?
Yeah, so we're just setting it up. Yeah, we could put in any function we want here. I just want to write down the form of how to integrate this. But yeah, we could. We don't know this f of x. Okay, so let's do the other order of integration. Okay, and now we actually have to be fairly clever here. There's a bit of a move that we have to do. Okay, so the first thing is to figure out where does y run. So this point of intersection is at 0, 0. And this point of intersection is at 1, 1. So if we're cutting in the y direction, we go between 0 and 1 as well. Okay, so that's good. We put 0 and 1 there. But now the question is, how far does x run? Right? Where does x go? Okay, so we need to figure out the bounds of x. Okay, so what we're going to do is we're going to solve for, I wish I had more space. Yeah, let's do it up here. Okay, so what we need is we need to solve for the x-coordinate in terms of y. So we're asking ourselves this question, how far does x go at height y? So we've got y squared is x, which tells us y is plus or minus root x. The only values that we see are these guys, the positive ones. Positive root x. So what does this measure? Okay, if we go on these horizontal slices here, then we're going to be traveling between x and root x. Okay, so I guess I should say what those coordinates are. So this is the coordinate right, so we're going between these two values here. Okay, so let's put that into our formula. Wait, no, that's completely backwards. Sorry, one sec. Sorry. Start over. Okay, what are our curves? Y is x squared, and y is x. Okay, those are our two curves. Okay, so we want to solve for x in terms of y. Okay, so what do? We've got y is x squared. We take square roots of both sides. We get this. We only care about the positive roots because we're only on the positive part over here. Okay, good. So what do these points look like now? So if we have one, then the x-coordinate also has to be y. Okay, so because on this line the x and y coordinates are equal, we might as well set them both equal to y. Okay, here, if we are at height y, so we're at height y, then the x-coordinate is going to be root y. Okay, much better. So now, the length of this thing will run from y to root y. Okay. Okay, very good. Yes, so what we have to do is we have to figure out the range of x values in terms of y and put them in here. Okay. So I would like to do one more example of this kind of setup. Are there questions about this before we go on? Okay, so we'll do one more example where we have to do this kind of inverting process and see how that looks. Okay, we're going to set up the integral of f of xy on the disk. Using that choice of area. Okay. So the region that we want is, oh, yes. Yes, this one. Yes. Yeah, good. So we start off here and we wind up, so we start off at y and we get to root y. Yeah, good. So let's do another one of these setups. Okay, so our region is the unit disk. It's got these guys as its top and bottom. So the integral dx dy will look something like this. Okay. So we're going in the y direction first. So y is traveling from -1, and we're cutting along slices in the y direction first, and we go from -1 to 1. And now we want to see how far do those slices go across. Right? What are the left and right endpoints of these guys? So we're going to solve for x in terms of 1. So we start off here. Right? We start off at equals to 1, because we care about the boundary of the disk. So we get here, and taking square roots, we go from negative 1 minus y squared to positive root 1 minus y squared. Okay, so the bounds of integration we want here are the ranges for x, so we get the following guy as our setup. Okay, very good. So I wanted to do a couple setups just to see how we decompose these regions. Very good. So we'll take a 10-minute break for questions, comments, and then we'll pick up at 10:10 and do some more actual integrals. Okay. Yep. Hello. Okay. So a couple people were quite observant, and I just wanted to point out a typo that several people found. Got to be careful with this stuff. Okay, so for this first setup, we're going from x squared up to x. Right? So we start at x squared and we go up to x. So these two bounds, which are in the notes, should be switched to x squared up to x. Okay, the bound in y that we start off at, the lower bound is x squared and the upper bound is x. Okay, so please make that minor correction. Okay. Very good. Oops. Okay, so I want to show sort of a hard volume calculation where we use Cavalieri's principle a little bit. So I want to do a volume calculation, and then we'll come back to this stuff about areas. Okay, so we want to find the volume bounded by these two cylinders. Okay, so here we've just got x's and z's involved. So y will vary freely over all possible values. And here we've got y's and z's. So x will range freely over all possible values. Okay, I like this example because it's very hard to draw. So we're going to go into drawing and see what we get. So recall Cavalieri's principle. Okay, and we want to integrate over z. Okay, so we're going to take slices in z and see what we get. The lowest value z can be will be negative r. And the biggest value that z can be will be r. Right? We're on these circles of radius r. So we get the following guy. Okay, so now we need to find the area. Okay, so to find what region in the plane we're looking at, we're going to solve for x and y. Okay, so what is this? This is the region in the plane given by the slice at z. So this is the Okay, so if we cut at height z, we'll get x and 1 like this. So what is that thing? It's a square. Okay, and the vertices of that square are given by these coordinates here. So we're going to get there's the bottom left corner. Bottom right. Okay, so here we've got positive x coordinate, negative y coordinate. Here. Okay. Okay, so our slice, every single slice of this thing turns out to be a square region in the plane having these dimensions. Okay, so all of these slices are squares with those side lengths. And from that diagram, we can calculate the area of the slice at z. Okay, the area at the slice of z, in one direction, its length is this minus this. Okay, so this is the length in x direction. There's the slice in the y direction. And we wind up getting this guy. Multiplying out, we get that the area of the slice is 4r squared minus z squared. Okay, so Cavalieri tells us that we can now find the volume. Okay, so we integrate out this guy for volume. We get something like this. Okay. Okay, so doing the arithmetic, we get 16/3 r cubed. I want to try, so we've done this just understanding the area of the slices, right? We haven't understood really the shape of the thing, but we've managed to find its volume. So the shape of the thing, quite hard to draw, looks something like this. Okay, so there's our there's y squared plus z squared is r squared. Now, in the other direction, we've got another tube coming this way. Okay, and these guys will meet at some small region in the middle. Okay, so the region where there's two tubes meet is the thing that we just calculated the volume for. Okay, but I think this is a nice application of Cavalieri. Questions or thoughts about how that calculation goes? Okay, I am now going to assume you're perfectly comfortable with this, and we'll proceed. Okay, so there's Cavalieri happening again. Okay. So there's one application of double integrals that I think is sort of unexpected but kind of nice. Okay, we can calculate area as the volume we can calculate area as the volume of a prism of height 1. So if we've got some region in the plane, right, we want to know the area of this circle. We've got area here, and we can extend it to an object of height 1. And then that area will get multiplied by 1 and become a volume. Okay, so it's sort of a nice way to think about area, think about calculating area, etc. Okay. Okay, so we've got this sort of standard problem. We started off our week by studying this problem. Now I want to phrase it as actually being a volume computation. Okay, now that we've got the machinery of regions in the plane and x simple and y simple and all that. Okay, we're going to sketch our region. I kind of want there to be like a math show taught by Bob Ross. Like I love sketching regions. It's probably why I got into this job. And wouldn't it be great to just have someone just sketch things all day? Anyway, sorry, never mind. So I'll draw the region. It's bounded by this guy and this guy. So we're looking for the stuff here. And we could do this using first-year techniques, right? We could integrate the length of the vertical slices. But let's do it using a volume computation. So the area, we can write it as the following thing. We can think of this as being our region R. And now we're going to integrate 1 over that region. Okay, so we wind up getting our bounds here go from -1 to 1. And then we go from this lower curve, which is x squared, up to 1. And now we're integrating the constant height function 1. Okay? We're integrating this function here 1. And we go like this. Okay. Okay, and now, so we integrated in y. We found an antiderivative for 1, and we get here okay, and now that sets up for us the integral that we would usually use from first year. Okay, the same integral that gives us the area of the thing, and I think that comes out to 4/3. Let's try. Okay, good. Okay. All right, so that's one way of calculating area using these double integrals that we've set up, is to calculate the integral of just the constant function 1. That'll give you the area you're looking for. Now, I want to come around to a theme that we've been sort of hinting at all week. Okay, which is this thing called Fubini's theorem. Okay, so if we've got a simple C2 function, or sorry, if we've got a C2 function on a simple region, then all three of these guys agree. So if we've got a C2 function on a region with simple boundary, then we can switch the order between dx dy and dy dx. And the volumes will come out being the same. I suspect probably one or two people here are going to go to grad school in math, a couple people, and you'll spend a lot of time talking about Fubini's theorem. I think it took our class like 3 weeks to prove, and it was just miserable. Anyway, so Fubini's theorem says we can switch order of integration. So let's see yet another example of how that would look. Okay. Okay, so let's set up and evaluate both of these integrals and see what we get. So our region is something like this. Okay, And then we need a function for this top line here to make it into a simple region. Right, we see that this line passes through this point. If we put in 0, we get 1. If we put in 2, we get 0. Okay, so that's the line there. And then this is the line y equals 0. And now we'll do both setups for this guy. Okay, so let's set up with dy dx. Okay, so x goes from 0 to 2, and y goes from 0 to a half, or 1 minus a half x. Okay, so there's our first calculation. Okay, substituting, questions or comments, thoughts? Okay, so substituting in the bounds. Uh-oh, sorry, I integrated in, right. Sorry, I was supposed to integrate in y first, but I integrated in x first. Have to be very careful. Yeah, so this first guy, the antiderivative should be happening in dy, yeah? Right, so I should first integrate in dy and get this guy. Okay, now when I substitute in 0, all these guys will go away, so I just have to substitute in my top bound. And I get oops. Good. this. Okay, now we'll collect up all the terms. Okay, so we've got these guys as our constants. Three halves there. Minus 3 halves x. Sorry, come again?
Minus 1 over 2x squared, maybe plus 2x squared.
This guy, minus by minus. Yeah, so that should be a plus. Good catch. It's good to catch these things early before we keep going. Okay, sweet. So we've taken care of the x's. Oh, and then there's a plus. No, wait, sorry. This one's minus. This one's plus. There we go. Is that better? Okay. Minus, plus, yes. Sweet. So now those guys give us negative 3 halves. Then we've got 4/8 minus an eighth. Okay, so we're there. Any questions or thoughts? Any other typos spotted? Sweet. Okay. Okay. So we'll take antiderivatives there. Yep, good. Okay, so finishing off the calculation. We get total volume 1, and Fubini is going to tell us the following fact. So by Fubini, right, no matter which way we do the integral, if we switch the order of integration, we're going to get the same volume in the end. Okay, so the details of calculating the second one, I'll leave most of the details to you. I just want to talk briefly about the setup of the second one. Okay, so to do the volume calculation in the other order, we want to go first in y. And just notice the way that I'm setting these up on the board. I look at this last guy and I think of filling in a big box here. So I write my outer integral, figure out where y is running. So y will run from 0 to 1. Okay. And now I have to figure out what's going on with the inner integral. So with the inner integral, I'm running along x, and I want to go from here to here. Okay, so I have to solve for that x coordinate. Okay, so now I know where my x coordinates will run. They're going to go from 0 to 2 minus 2y. Okay. Wrote x twice, thank you. So I want the y on the outside. Sweet. Okay, so the details of doing the second calculation I leave up to you, but I think the tool of being able to set something up in both ways is very key. And we're going to do a couple more examples of that next week. Okay. Okay, so I'd like to finish things off with this summary of what happened this week. Okay, so what were our major themes for the week? Yeah, indeed, for sure. Okay, double integrals, Cavalieri's principle, okay. Yeah, Fubini's theorem that we can switch order. Yeah? Yeah, simple regions. Okay, any other thoughts or techniques that came up? Major concept? Okay, I really just want to put it on there because I was so jazzed about it. Okay, the volumes of the hemisphere and cone add up to the cylinder by Cavalieri. Okay, so I think that's pretty accurate. We didn't do too much technique-wise. Very good. So I'd like to finish things there, and if anyone has questions about homework or whatever, you're welcome to come up and ask now, okay? And then I'll head over and have office hours.